Hi, everyone. Thanks for joining. Hey, Lizzie's here. Awesome. We've got the Alex Crawford fan club out. This is great. Hi, everyone. Thanks again for joining another episode of the ongoing IGS Global Seminar Series. This week, we have Dr. Alex Crawford, an assistant professor here at the University of Manitoba, who's focused on studying sea ice. Alex is going to give a talk entitled Pauses in Arctic-Wide Autumn Sea Ice Expansion. Alex is actually just a few doors down from me, so this is a little bit funny. As per usual, the seminar will be recorded and posted on the IGS YouTube page in the coming days. We ask that you save questions till the end. You can either hold on to them and raise your hand at the end or drop them into the chat box, and I will bring them up at the end. We only have one presenter this week, so we have quite a bit of time for discussion and questions at the end, so please feel free to ask away and open it up. And without further ado, I will pass it over to Alex.
Thanks, Dave. So I think that first, let us make sure that I am sharing the PowerPoint correctly. And then going into presenter view. Then Dave, could you just give me a thumbs up if that's working? Fantastic. All right, thank you. And thank you everybody for being here today. Before I start, I do want to acknowledge that I'm on the University of Manitoba campus right now, and that is in Treaty 1 territory in Canada, which is located on the original lands of the Anishinaabe, Aninawak, Anisinaninawak, Dakota Oyote, and Dene peoples, and the national homeland of the Red River Métis. And I also would like to just say, before we really get started, that this sort of project right here is what I think is some of the best science that you can do, because it was motivated by curiosity. It was a fun thing to do, and it only took 13 months between me having the question and then actually getting accepted at Journal of Glaciology. So this is something that I'm really excited about. I think it's really fun to look at. And then for all of you who don't just have the innate curiosity, I think there's some really cool implications about how Arctic sea ice is responding to climate change writ large that come out of looking at this sort of research. And then I should also acknowledge my co-authors, Clement and Julianne, for their help with working all of this. And I think with that, let's dig into pauses in Arctic-wide autumn sea ice expansion. And I'm going to start off with talking about a little bit of context here. When you're at IGS, I assume that a lot of you, if not most of you, have some familiarity with this idea that sea ice not only exists, but is highly variable throughout the year in the Arctic. And if you look on the map that we have on the right, that's an example of 1 year of what the seasonal sea ice looks like. The really bright, kind of light-colored whitish gray, that's showing you how much sea ice there was at the yearly minimum in the middle of September. And then that lighter blue color is showing you how much sea ice there was at the maximum extent, which occurred about 6 months earlier, back in March. And the difference for 2023, which is pretty typical for nowadays, was that there was about 4 million square kilometers in September, and it expands out to about 14 million square kilometers in March. Now, back in the 1980s, there still was less sea ice in summer and more in March, but the numbers were different. There's about 7 million in September and about 15 million come March. So that means that we do have to adjust for climate change if we want to start thinking about the growth of sea ice, the expansion of sea ice over the course of the autumn and the winter. And so on the graph on the left, what I'm showing here is if we just took that minimum day of sea ice extent and we call that 0, that's like our starting point for how much sea ice there is in the Arctic. And then we looked at how much sea ice there is compared to that each day of the year, we can see how much sea ice growth we tend to have over the course of an autumn and winter. And then we can see the decline happening over the course of the spring and summer. And so again, you see that there's going to be this shift from about 8 to 10 million square kilometers, depending on the year you're looking at, between that summer minimum and the winter maximum. And that's some good context, but I want to talk about pauses in this expansion. And so to do that, I think it is useful to look at daily sea ice extent and have a little bit of an animation go. So this animation from NASA, which I really love, is showing us a few things. The really bright colors is showing you multi-year sea ice that's at least 4 or 5 years old. And then the kind of dullest grayish blue color is showing you the first year ice that is just growing in that one season. And we're going through multiple years. And again, like I said before, you can see the expansion of the sea ice in the fall and the winter, and then you can see the contraction going back in the spring and summer. But if you start focusing on a few different regions, like the Bering Sea or Baffin Bay, you start to notice that that sea ice edge doesn't just expand monotonically toward the south. There are some days when that sea ice edge will stop. It might even go back a little bit and then jog forward again. And so we know that if we look regionally at sea ice, there are plenty of times when that sea ice edge can move around. It can be pushed back. It's not always going forward. And after you look at this enough years, enough times, you might start to have the same question that I had, which was Arctic-wide, are there ever pauses? Are there ever pauses in that Arctic-wide expansion of sea ice extent in autumn? Or is it always just this small regional thing that's compensated by growth somewhere else? And of course, the answer to this question is yes. I wouldn't be giving this talk if the answer turned out to be no. But I do think that there are still some other interesting research questions that we can get to after answering that initial one. So starting with the basic thing, are there ever pauses in this Arctic-wide expansion of autumn sea ice extent? And if so, how often do they occur? When do they occur? Why do they occur? And then, of course, the question we always have to ask with anything Arctic nowadays, is there any climate change signal to any of this? So I'm going to walk through all 4 of these, the first one pretty quickly. But in order to do that, I do need to do one other thing, and that is provide a small amount of data and methods. And I do mean a small amount. This is going to be brief. So if you want to get into some nitty-gritty details, I am more than happy to do so in the Q&A period. But really, we just need to define what I really technically mean when I say a pause in the sea ice extent expansion. So the way that we're doing it with this work is based on a 6-day discrete difference. So what I mean is we're going to look at the sea ice extent today, and then we're going to look at the sea ice extent 6 days from now, and we're going to see whether it's higher, lower, if so, how much. So just what's the difference in the sea ice. A lot of people like using 5-day moving averages with Arctic sea ice extent, and if you did that, you're going to end up with very similar results. There's very little error in that, so this is a pretty good, robust metric. Another thing that's important to note, why 6 days, what's good about this time scale? It's also robust to some short-term data gaps, especially in like the 1980s. The sea ice record that we have was actually every other day for a while. And even today, there are times when we have missing data in certain pixels from the passive microwave satellite record. There are also some days that are just completely missing because of retrieval errors or other issues with the satellites. So having it be about 6 days gives us a good measure that's not very sensitive to those kind of small, little noisy things that might happen. And then the other thing I need to say is a caveat. There is some sensitivity to the sea ice retrieval algorithm you use. Now, if you want a good climate record, there's really nothing better than having passive microwave satellite records of sea ice concentration for this sort of work. But not every algorithm is the same. My favorite one to work with for doing a climate-related study that's covering many decades is the NOAA NSIDC Climate Data Record, or CDR. And that one is actually built from looking at both the NASA team algorithm and the bootstrap algorithm, which are 2 widely used ones. And it's actually always taking the maximum sea ice concentration between the 2 of those for every grid cell. And there's a lot of good reasons for that I'm not going to dig into the details of right now. But the thing that is important to note is that there is some sensitivity to whether you just use the NOAA NSIDC CDR, if you use the NASA team algorithm, if you use the bootstrap, about what you would count as a pause or not. So again, in order to make sure we have a nice robust metric that is going to be looking at events that are definitely pauses in sea ice extent expansion, we decided to be fairly conservative. We said that all 3 of these algorithms need to be showing us that the 6-day discrete difference in sea ice extent is less than 0.1 million square kilometers, and at least one of them needs to be at or below 0. And if all of that's true, we're going to call it a pause. And then the last thing methodologically that I think is really essential to know is that there are sometimes there might be consecutive days that meet the above criteria. And in that case, we're going to count it as one event. Sometimes it's useful to talk about the number of days that are the beginning of a 6-day pause, but other times it's really going to be more appropriate to talk about these as single events. So with that very brief data and methods out of the way, let's get to some results. So here they are. This is a plot that is showing you year on the x-axis, and then you're seeing the day of year on the y-axis. October 1st is up at the top, and then we're getting to November, December, January, February, March on the way down. And the blue is showing you everywhere where there is a pause in that sea ice extent expansion going on. This has never happened in October. Not a single time, and not even if you just choose one of these algorithms, can you find an event happening in October. So it does not occur. It's rare in November and December. So in the rest of autumn, it's only happened 13 times for a total of 24 days. That's less than 1% of all of the days. So these definitely count as rare events in autumn. By the time you get to February, though, this is a really common occurrence. About 25% of days in February are pause events, which means, roughly speaking, you'd say about a quarter of the days in February will have higher sea ice extent than 6 days later. Okay, so why does this happen? Why do we have this case where you go from none in October, a few in November and December, more in January, and then it's common in February? Well, it really just comes down to this basic idea that the average rate of sea ice extent growth slows down throughout the autumn and winter. In October, the average rate is about 0.55 million square kilometers per 6 days. In November, it's down to about 0.45. By the time you get down to February, it's right around 0.1 million square kilometers. And you can also see that if you just look at that curve of the mean rate of sea ice extent. If you look at the curve of the mean sea ice extent, and you can kind of see that the mean rate is getting slower and slower as you get closer to the maximum. So in other words, the faster the sea ice is expanding, the less likely it is that any synoptic scale variability is going to bring it down to zero. And the slower it's expanding, the more likely that is. This makes perfect sense. So it's very logical why we see this, that it's a rare event in autumn. But that also means that autumn is probably the time that we're really interested in explaining why it happens when it does, because that's the only season of the two that it really is a rare event. All right. So getting over to our research questions, we actually can answer 2 of them already. Number 1, are there ever pauses in Arctic-wide expansion of sea ice extent in autumn? Yeah, it does happen. Cool. But how often? Well, it happened 13 times over the course of 45 years. So that means it's on average less than once every 3 years. This is a rare sort of event, and it is worth trying to explain why does it occur. And that's actually what the largest portion of this talk is digging into, because I think there's some really fun things to drive at with this. All right. So in order to understand why, first, I actually want to better understand where. And I'm not going to show you every single event. I'm just showing you the first 5 that happened in the record because they were the first 5. And on this series of maps, what I'm showing you is white is stuff that's ice covered the entire time when there's one of these pauses. The open water period, the open water is in light blue, and that's for the entire period, open water the whole time. The gray is land, as you may have guessed. But then the other 2 colors, green and magenta, those are the ones that are interesting to us. The green are the areas where there is ice growth during one of these pauses, and the magenta is where there is ice loss. And because we're talking about pauses in autumn sea ice expansion, then that means that there has to be basically as much magenta, if not more, than there is green, because we are experiencing either loss or complete stagnation. All right. So if you look around, you may notice that one of the areas where you often see the sea ice edge is over in the Bering Sea or the Sea of Okhotsk. And I kind of group those together as saying that's the Pacific sector of action here. That's one of the places where the sea ice edge is, and so that's one of the places where we might be losing the sea ice that can lead to one of these pauses. Sometimes that can even be up into the southern Chukchi Sea if it's happening in November, but usually it's the Bering Sea, Sea of Okhotsk. Another area that is important is Eastern Canada. There's just about always a sea ice edge somewhere in the Labrador Sea. Sometimes it is all the way up into the Baffin Bay. And at times, but not always, there is a sea ice edge in Hudson Bay, which you can see in that 1984 example in late November. And then finally, there's the Nordic sector. This is where we have the East Greenland Sea, the Barents Sea, the Kara Sea. That's another area where the sea ice edge always is present, except the Kara Sea, it's just sometimes there, but always in the East Greenland and Barents Sea. So that's another place where if there's sea ice loss there, it might be leading to one of these pause events. Now, I think these maps are fairly small, so if you don't have a big screen, it might not be super easy to see all of the results. So rather than kind of walk through a map for each and every one of these pauses, I'm going to summarize it all in one diagram. So what I've done here on the left is I have shown you a bar that is indicating whether there is sea ice growth or sea ice contraction and loss in each of those three key sectors. The green is the Pacific sector, the blue is the Nordic sector, the orange is the Eastern Canada sector, and then red is anything else. So if we take those definitions, we can see a few things here. Number one, for each of those 13 events that's happened, you can see that there are a lot of blue bars pointing to the left and only 2 that point to the right. Yeah, so that means 11 out of 13 of our events have sea ice loss occurring in that Nordic sector. In other words, that's the area that we should be paying most attention to if we want to understand why these things happen. There are 4 cases when there is substantial loss in the Pacific and there is also loss in the Nordic sector. And there's 1 case where it's really just the Pacific that is seeing the loss. And then there's December of 2010, which is the only case where there is loss occurring in Eastern Canada. In every other event, the other 12, there was actually growth occurring in that Eastern Canadian sector. So 2010 is a bit of an outlier, a bit of an oddball. I think we'll have time to dig into why, but we want to pay most attention to the other 12 events, especially the 11 that are focused on that Nordic sector. And the other thing that I can say is if you just look at what is the distribution of all of the possible 6-day changes in sea ice extent for each of these sectors, and then you make those little whiskers to show how far the range can be, the Nordic sector is showing us that that is the one that is most likely to be seeing a sea ice loss. And the Eastern Canada sector is the least likely to be seeing that. So this kind of lines up with what we would expect. The Nordic sector is more variable. It's more likely to have these loss events occur in the first place. So it makes sense that it would be the sector that's really driving loss in Arctic-wide sea ice extent. The other thing I want to point out, that Eastern Canada sector has exactly 1 time in every autumn for 45 years where it was losing sea ice over a 6-day period. It's December 14th to 20th, 2010. So again, that one is just crazy compared to everything else. All right, so we're going to explain why we want to focus in on the Nordic sector. So let's take a look at an example event that helps illustrate what's going on, what's leading to all of this. The example we're going to pick here is 1990 because it's one of my favorites. And the one other thing we're going to do for the people with smaller screens is we're going to zoom in on that map because we really just care about the East Greenland Sea and the Barents. Yeah, let's zoom in on all those maps. There we go. That's going to make this a little bit easier. So this event was entirely from the Nordic sector. The Pacific and the Eastern Canada sector both actually had a little bit of growth of the sea ice edge here. And if you look at the first panel on the upper left, that is that same sea ice tendency map I showed before. And you can see there's a lot of magenta in the East Greenland Sea and the Barents Sea. So that's where all this loss was happening. If you go over to the upper right panel, that is showing us sea ice motion with those vectors. And it's also showing us the convergence or divergence of sea ice. So anywhere you see green, that's where sea ice was diverging. Anywhere you see purple, that's where it was converging or coming together. That magenta line is showing you where the sea ice edge was at the beginning of the pause event. And you might not be able to tell because it's almost all white, but I actually am showing you sea ice surface temperature anomalies on this map as well. There just really weren't many strong sea surface temperature anomalies for this particular event. But what there was a lot of was sea ice moving away from the sea ice edge, moving away from the Barents Sea toward the north of Greenland into the Beaufort Sea. You see a lot of that purple or convergence north of Greenland and in the Beaufort Sea. So in other words, we more or less were reversing the transpolar drift and just shoving the sea ice over back toward the Pacific sector. And that can explain a lot of what was going on with reducing the sea ice in the Nordic sector. The other thing, though, is that it was also a good bit warmer during this period in the atmosphere, although not the sea surface temperatures. And if you look at the lower left-hand map, that is showing us the net surface energy balance and its anomaly. The anomaly is in the colors. So anywhere you're seeing that red color, that is showing you a positive anomaly in surface energy balance. And up around Svalbard, where that sea ice edge was, it was in excess of 200 watts per square meter in some places. That is a strong positive anomaly. However, it is notable that the net surface energy balance was still negative, meaning it was still upward. That means that the surface was still losing energy to the atmosphere, at least according to the data set here, which is ERA 5, keep in mind. So this is a reanalysis data set. I don't have a lot of in situ observations for this event. In other words, this implies that we probably weren't melting a lot of sea ice here. It was really more of a dynamic story. We were shoving the sea ice back, and that's the main reason why we had this pause event. However, do note that if you are losing a lot less energy than normal from the surface, that might be a sign that the sea ice growth or recovery would be slower than you might expect otherwise. Okay, so if we put those things together, we can take one more step and say what's going to cause the sea ice to be moving back away from the sea ice edge, going to cause the temperatures in the atmosphere being a lot warmer than normal. And the answer to that is most easily observed if you look at that bottom right-hand map, which is showing us the sea level pressure for this period and the 10-meter winds. These aren't anomalies. These are just straight up what the sea level pressure and the winds were doing. And you'll see that the Icelandic low was especially active. It was also shifted a little bit more to the north than normal. The sea level pressure was down well below 968 hectopascals, which for the atmospheric scientists in the room, they should appreciate, yeah, that's a pretty low sea level pressure, even for the Icelandic low region, which has a lot of cyclone activity. And the winds were from the south or southeast throughout this area. And so it makes a lot of sense then why you would see a lot of the sea ice getting shoved to the north of Greenland and converging there. Now, we can dig into this a little bit more, though, and I think it's worth it because these are 6-day averages. So that doesn't just mean you had one cyclone down below 968 hectopascals. That means for 6 days, the average sea level pressure was down below 968 hectopascals. That is super low. That is in the 0th percentile of sea level pressure for autumn in this area around Iceland. And there's quite a few maps sitting right here. If you pay most attention to the top row, that is showing you, again, sea level pressure and what the wind is doing. And then there's a yellow dot for the center of all the cyclones. On the lower plot, especially if you know some atmospheric science, I'm showing you the geopotential height. So you're looking at where there's troughs and ridges at kind of the mid-level of the troposphere. And I have the yellow dots again for where the cyclones were located. And then I have blue lines to show you the full track of the storms with a little X marked for where it started to give you a little bit of orientation. And then what I did was I took 3 different snapshots. Christmas is on the left, December 28th is in the middle, December 29th is on the right. And if you look at these enough, you'll start to realize, oh my gosh, that's several different storms. It's not just one. In fact, there were 4 different extratropical cyclones that passed north of Iceland and up toward the Fram Strait, although not all of them actually made it all the way to Fram Strait. And that is what we call serial clustering or temporal clustering of extratropical cyclones. There's 4 of them that all took basically the same track to sit just north of Iceland. A few of them hung out there for a while. And 3 of those storms were abnormally strong, stronger than the 80th percentile for cyclone intensity. 1 of them was the 2nd strongest on record, so that makes it stronger than the 99th percentile. This just wasn't a lot of storms. It was a lot of strong storms. And then the last thing I'll mention about this atmospheric setup is that there is some evidence of blocking in this situation over Scandinavia near the beginning of the event. And that's another thing, atmospheric blocking, that seems to be present in a few other events if you start paying attention. So that's just 1990, but I use it because it's emblematic of what's going on for a majority, a strong majority of these events. This is part of a figure from the paper where we were looking at what was the percentile for temperature, for surface energy balance, for the winds, for each of the 13 pause events that happened. And then we looked at several different regions. For the talk here, I want you just to pay attention to the Barents and Kara Seas and look at the distributions there. 925 hectopascal temperature. The Barents and Kara Seas are sitting most of the time for most of these events, not just warmer than normal, but well warmer than normal, up or over the 67th percentile in the upper third. And several of them are actually extreme. Similarly, for the surface energy balance, most of them are sitting up in that upper third of surface energy balance, so much less upward than normal. And the meridional winds at 10 meters, so this is saying that if it's positive, if it's a high percentile, in other words, it's southerly. Again, up in that upper third for most of these events. There's an outlier for a few of them, but most of these events are sharing this common feature. So if we kind of summarize all of this, if you want to understand why Arctic-wide there's going to be a pause in the expansion of sea ice extent in autumn, you look to the Barents and Kara Seas, and you look in particular at events that are having these strong positive surface energy balance anomalies, strong southerly or southeasterly winds, temporal clustering of abnormally strong cyclones going through the same location, 3 or more. And oftentimes there's high pressure sitting to the east. Sometimes it's even able to be classified as an atmospheric blocking event. And that we've seen case studies in papers of this sort of thing before, leading to changes in sea ice in places like the Barents and Kara Seas. But now we can be pretty confident that, yeah, these are big enough. They're big enough events. They can affect the Arctic-wide time series and history of what the sea ice extent is doing. There are 4 events that show a very similar setup in the Pacific sector atmospherically that can help explain this in a similar way. And then there is one very weird case in 2010 that I have mentioned enough times that I really need to show you. All right, so this again, this is an outlier. This is a single case. It's a unique case, but it's kind of fun. Like we did before, let's zoom in on the area that really matters for this. In 2010, if you look at what the sea ice tendency was like, in the East Greenland Sea, it's interesting. There's a little bit of loss on the eastern edge of the sea ice pack there, but then there's expansion. There's actually a good bit of growth down at the southern tip. That's interesting. File that one away. But then you might notice that there's a little bit of loss in Baffin Bay, Labrador Sea area, and there's a lot of loss in Hudson Bay. So in other words, Hudson Bay, more than anything, is driving this. Okay, why? Well, first, let's take a look at the sea ice motion and the convergence. If you look in the East Greenland Sea, you can see there's very strong flux of sea ice through Fram Strait down into the East Greenland Sea. That helps explain why we're seeing a gain down at the southern tip there. Okay, now if you look at Hudson Bay, the sea ice was moving east to west. If you start to look at the overall pattern there, it's a little bit broken up because of the land, but it's basically clockwise rotation of the sea ice. Oh, that starts to tell us what's going on. All right, the lower right-hand panel, I'm showing you the sea level pressure again. It's like the opposite situation we had in 1990. It's not really low pressure, it's really high pressure. Greenland is pretty well known for having a lot of high pressure be common, but in this case, Baffin Bay was also straight under a really large area of very strong high pressure. This is actually the record strongest high pressure over Baffin Bay in autumn that we have for the whole 45 years of record. And it was also the strongest easterly winds over Hudson Bay in autumn for the entire record. Interesting. All right. Now, there's one more piece to the puzzle, and that is perfect timing. Because even if you have really strong easterly winds over Hudson Bay, if they happen in October, you're not going to change the sea ice extent. There's no sea ice in Hudson Bay in October. If it happens at the end of December, well, then you might be in luck. Because on average, it takes about 20 days for the sea ice to expand from the northwest side of Hudson Bay all the way across to the east side. So if you can have really strong easterly winds occur when that sea ice edge is partway across in that less than 3-week period, you might be able to make something happen. And that's exactly what happened in this case. The sea ice had gone about 2/3 of the way across Hudson Bay. You have the strongest ever easterly winds over Hudson Bay, and it shoves the sea ice back. By the way, Hudson Bay typically has northwesterly winds, not easterly. So just the fact that the direction was flipped is an anomaly, but it was the strongest anomaly we ever had. And this alone would be pretty good for explaining why there would be a pause here. Now, on top of all of that, if you look at the sea surface temperature anomalies in the upper right-hand panel, or you look at the air temperature anomalies in the lower left panel, you can see that it also was really warm over the North Atlantic this year, and it was very warm temperatures then going over Hudson Bay. So again, it's not just a dynamic story. There clearly is something going on with the thermodynamics, even if the main explanation is that we shoved the sea ice back rather than melted it. All right. So with that in mind, we now can go backwards, apparently. Excuse me. We now can go up to our research questions again, and we can answer the question, why do they occur? Serial clustering of strong extratropical cyclones, often with blocking, is usually the explanation, and it's usually for the Nordic sector, sometimes in the Pacific. Then there's this one outlier case of something that was unique that had never happened before. But we also want to answer the question, is there any climate change signal here? I actually had a hypothesis that was totally wrong when I started this research. This is one of the things I think makes it interesting. There was a surprising outcome right here. If you were paying close enough attention to when I first showed this graph, you may have already noticed there really isn't that much change. These pause events are really just as common today as they were back in the 1980s. If you run a Mann-Kendall test on this to look for a trend, the p-value is 0.51. If you go for the number of pause days, if you do the number of pause events, same deal. If you look at February or January instead of autumn, same deal. There really is no change. They are not more common. They are not less common. But the interesting thing, I know that sounds like a downer, but the interesting thing is why there's no change, because like everything about Arctic sea ice has been changing over the course of the past 40 years. And the answer is that there's really two competing trends that are occurring at the same time. One of them is that the sea ice is growing faster on average than it used to. This is a graph that shows the total amount of growth in the months of October, November, and December. Before 2005, on average, there would be about 6.5 million square kilometers that would be gained in sea ice extent in autumn. Since 2005, it's 7.6 million square kilometers. To put that in the units that I've been working with, that's equivalent to 0.43 million square kilometers per 6 days, or 0.5 million square kilometers per 6 days, or a 16% increase. So if you make the average rate of sea ice growth faster, then that means it's going to be harder for it to ever get down to zero. If you just think about the normal variability that you're going to have around those numbers, it's going to be less likely that you get to a pause. But that's not the only thing that's changing. The other thing that's changing is the variability. The variability of that sea ice expansion growth rate is also going up. Before 2005, it was about 0.22 million square kilometers per 6 days. That's the standard deviation. And since 2005, it's been about 0.26. That is about an 18% increase. These are close enough. They roughly cancel each other out. Because if you have a more variable sea ice extent growth rate, you'd expect it to be more likely that you get to a pause, that you get to a point where it isn't actually expanding. It is interesting to me that these are really more step changes rather than linear trends. And 2004 to 2005 is the change point for both of those. If you use a Rodionov test, I also used a Pettit test if you are used to regime shift or change point analysis. And the last thing that's worth mentioning about this is that, yes, some of you might be thinking, is that related to sea ice thickness? Yeah, it definitely does seem to be. We looked at whether there were any changes in atmospheric forcing. There really aren't, except for in the Sea of Okhotsk. It's the only place where you have any chance of that being an explanation. But sea ice thickness absolutely can explain why some of this might be happening. There's a few different data sets that I'm throwing at you right here to try to give evidence for the point. In the first plot, we're showing measurements specifically of sea ice thickness. This comes from Cryosat-2, from ISAT, from ISAT-2, and then more recently, there's a product that my co-author Clement is responsible for, trying to extract sea ice thickness from the passive microwave record directly. And if you take a look at those, it's hard just from like ISAT, ISAT-2, or Cryosat-2 to say whether there's been a big trend since the 1980s or 1990s, because we don't have a long enough record, but at least from the passive microwave record, you can see that, yeah, there is a decline in the sea ice thickness, and 2004 to 2005 really does represent a shift to a new regime. ISAT also does show a pretty big drop in that year, so that's enticing, but again, not a long enough record to be statistically confident. And then on the right, proxy for sea ice thickness is the sea ice age. Older sea ice tends to be thicker. So do we see a trend in the sea ice age? Yes, we know that we have from a lot of different papers that have talked about this, sea ice age has been going down. And depending on how you measure it, you may find that there's a change point in 1989. You might find that there's a change point in 2002, 2004, 2006. Again, depending on exactly how you measure things, but there's a lot of change happening right in that period of the decade of the 2000s, between about 2002 and 2007. And so again, this is some pretty good evidence that around the time that we're seeing this increase in the variability of the sea ice expansion growth, we're also seeing a decrease in the thickness and age of the sea ice. In other words, this idea that thinner sea ice is more responsive to any atmospheric forcing is probably heavily involved in that one component of the sea ice change that is influencing the fact that we actually don't have a big change in the frequency of these events. So to summarize, is there any climate change signal here? Surprisingly not. I thought there would be one way or the other. But this higher variability in the rate of sea ice expansion is being counteracted by there being a faster average in the sea ice expansion. And so with that, that answers all the research questions. So I'd like to thank you all for being here today. And I hope we have enough time that we can dig into some details or ask some questions or tell me I'm crazy.
Excellent. Thank you very much, Alex. You're not crazy.
Thank you, Dave.
Okay, we'll open it up to David Bailey has a question here. Dave, do you want to unmute and read out, or do you want me to?
Well, I can maybe summarize. I just wanted the details down. I mean, it's just like a little semantic issue. I think of a pause as, it's a slowing in the growth. So near that peak in March, the tangents flatten out.
Mm-hmm.
And, so I think of that as a pause in the sea ice edge. And I'm reminded of Mike Steele's lingering idea, because there's a similar sort of thing in summer where it melts back and then it kind of sits there for a few days and then it melts back again in just sort of these jumps. But I don't think, and maybe this is my misunderstanding, I don't think you were really talking about that sort of thing. I think you were talking about ice loss during periods that would normally be growth. Is that right? Or
yeah, that's how I would describe it. And so one of the things, like you said, yeah, we expect that there should be plenty of times when the sea ice is just kind of lingering or pausing when you're up near the maximum or down near the minimum. So there really isn't much to write home about, because that's just what we expect. That's normal. Sure. And so what we were more interested in is when it happens at a time when you expect there to be more steady growth, what is leading to that? And I wasn't even sure if it ever could happen in October, November, December. And the data says it never has in October. Not saying it couldn't, but it never has. And so again, like you expect that, yeah, there's only 3 events that happen in November, and there's 9 that happen in December, and then it grows from there, getting into January and February.
Richard Alley compliments you and then has a question about what happened in Eastern Hudson Bay this year.
Thanks, Rick, for plugging a place I care a lot about. So yeah, Eastern Hudson Bay, unfortunately, I don't have great slides that show what was happening with Eastern Hudson Bay at the moment up here. But in Eastern Hudson Bay, there was really early sea ice retreat or loss. It started happening in early May. And that is much sooner than we typically see. It was actually a record earliest that you ever lost the sea ice in Eastern Hudson Bay. And the reason for that ends up looking pretty dang similar to what happened in 2010, the exception being that it's happening in May as opposed to happening in December. And rather than temporarily stalling the advance of sea ice across Hudson Bay, it was accelerating or initiating, really, an early loss of sea ice in Hudson Bay. So when I say it was similar, again, there were really strong easterly winds. And if you just looked at the month of May, May 2024 is the May with the strongest easterly winds in Hudson Bay. And so a similar sort of setup happened, but it has a different consequence because of the state of the sea ice at the time it occurred. And there's two other notes that I think are interesting talking about that. One was that it actually was relatively late retreat of sea ice in western Hudson Bay. Because again, this is mostly a dynamic story, not a thermodynamic one. So you took that sea ice that was in eastern Hudson Bay, yeah, shoved it away earlier than normal, but then it just hung out. In western Hudson Bay, there was still a fairly large ice flow into August this year in western Hudson Bay. And then the second thing that's notable about what happened this year is that the sea ice took a long time to reform in Hudson Bay. It was very delayed. And before this year, 2010, was the latest the sea ice had ever reached the eastern shore of Hudson Bay. And then this year, I think, depending on how you measure it, either just about tied it or broke it and beat it. So in other words, this event here back in 2010 was previously sufficient to make it so that Hudson Bay had the latest advance that it had ever experienced all the way across to the edge. And I'm saying all the way across the eastern shore. But this year, just because of how early the retreat happened, how warm the summer was, how much heat was able to be taken up by the ocean and generate these marine heat waves that delayed the sea ice reformation in Hudson Bay, or freeze up in Hudson Bay, late enough that it actually countered the 2010 event and challenged it for the crown.
Excellent. Emily, this has been really great to learn about. Not much question really, but the way you talked it through was really engaging. Do you know more? Do you do more webinars or lectures? Also, do people getting into this area? Somebody who is still studying pre-PhD, how do you recommend people getting into this area? Maybe a bit of a bigger question about research.
Getting into this area. So getting into things like sea ice. And I think my number one recommendation for somebody who wants to just get into this sort of science is look at the data all the time. So for me, one of the reasons why I noticed there might be something going on here that I was interested in was I look at NSIDC's Sea Ice Today page a lot. I look at I look at Zach Loeb's stuff a lot. Sorry, Zach Loeb's stuff a lot, because he has some really good visualizations of sea ice and other stuff. So just look at the data, see what's going on. You'll be curious about something, and maybe you'll start looking it up, and you'll find that there's really good information about it already. Sometimes you might find there's a little bit of a data gap. Even if it's a niche project like this one, it still can be really fun to do, and you still might reveal something interesting about the way the climate system works. I think this works also like looking at satellite data. If you're interested in anything from ice sheets to geomorphology to atmospheric science, there's lots of satellite data. There's lots of weather forecasts that are always being produced that you can always go and look at. Now, that is just to get the curiosity going, obviously. And the other element of this is, well, you need a position to go and do it. And so in order to make that happen, coming to seminars like this, meeting people, getting to know their names can be really helpful. Going to conferences can be really helpful to get to know people that you might want to work with. And so that's another recommendation that I have. It does take not being shy, and asking a question like you did is great. I know that I, as an undergrad, was way too shy, and it took my advisor convincing me to go to a conference to start to break out of my shell. And so definitely do that if people are nudging you toward any sort of networking.
Yeah, great answer, Alex. Emily, I dropped a couple links there for the NSIDC Sea Ice Today page, and Zach's page is fantastic. It provides real-time updates on sea ice, different ways of looking at sea ice, and highlights some things that do jump out every so often and can kind of spark that interest.
Yeah, and I mean, if other people have other websites they want to point to with good data and visualizations, there's others I could go on about.
Yeah. Richard has a follow-up. For your most common pauses in the North Atlantic, would there be a signal in a Greenland ice core? Or is the resolution?
Yeah, that's a good question. I mean, the resolution on what I'm looking at here is really synoptic scale. I'm not sure that you would get it unless there was I don't know what the correlation is with like the snowfall or the type of snowfall that's happening on the top of the recent ice sheet. Or with all of these, they do tend to have some warmth to them. So whether there might be, if melt events would be common with them, with the really extreme ones, maybe you might be able to see something, but I don't know quite enough about the ice cores. I think Richard Alley might, to give a great answer to that. Yeah.
Well, Richard was the one who asked that question. So
I know. That's why I'm like, ah.
Alex, could you jump back to the slide where you show the seasonality of these pauses?
Yeah, you mean just kind of the basic figure that just shows where all of them are?
Yeah.
Yeah.
I guess it's just interesting that there's essentially none in October, November, a couple in December that really highlights that once you reach that sea ice minimum and sea ice starts to form kind of out from the central Arctic, it just grows so fast that it isn't until it gets into these peripheral seas that you can really get sort of slight changes that offset it and cause it
Yeah, no, that
to level
yes.
out.
Yes, no, thank you for bringing that up, Dave. That is a great point. And one thing, when I was first looking at this, I actually tried to do the analysis at first, framing it based on the location of the sea ice rather than dates. And I thought that that might be really important, that you'd expect the sea ice can grow really well until it starts getting confined by the Siberian coast, Alaska, and now you have like narrower zones where the sea ice edge is. And maybe that would explain why you get pauses or why you don't. And in doing all of that, it turned out that what I ended up finding was that didn't quite work as well as I would have expected. And the much cleaner analysis was just looking at the timing and just looking at what month are we in. And that was one of the reasons why I also thought there might be some climate change signal here, because we know that there is a climate change signal on where the sea ice extent is in every month of the year. So I still think that in a vacuum controlling for everything else, then that the idea of how basically how many linear kilometers do you have of the sea ice edge should make a difference for how likely this is to happen or not. If there's a shorter distance, it seems like it shouldn't take as much of a unique atmosphere to make a change, but it hasn't come out in the data yet. So that was a surprising thing too.
Yeah. Yeah, it's super interesting.
Yeah.
Dave, you have your hand up again.
Yeah, I mean, I'm happy to go with other people, but things keep popping into my head. So I have kind of a two-parter for you.
Okay.
So I wonder, is there a relationship maybe between these pauses and the seasonal predictability aspects?
Mhm.
You see anything there from year to year where, years with more or less pauses maybe show some predictability later in the season? And then the other part is, what about the Southern Hemisphere?
All right, yeah, Southern Hemisphere. Okay, so the first one, we did look a little bit at the first one, not at all the second one. So on the first one, I was hoping that there might be some good story that I could tell of saying, like, if this happens, it's going to have some implication on, like the seasonal maximum that you might see. And it does seem like the sea ice recovers pretty well, and there isn't a significant correlation between like what the sea ice is going to be like in the middle of March and whether one of these events has happened or not. So it does seem as though, from a seasonal standpoint of predictability or forecasting, I don't know that this is really that important. I'd love to say it is, but I don't know that it is. I haven't done a lot of work, so maybe there's more there than I realize. What I can say is that if you're trying to do a forecast of like week to week, then there's plenty of utility with this, because it does take more than those 6 days for the sea ice edge to recover regionally. Now, that means that we're not really concerned about Arctic-wide sea ice extent expansion at that point. We could just go back and start talking about regional variability of the sea ice edge, where, again, a lot of these same atmospheric forcings are going to be important. And especially in the Nordic sector, we could say, oh, this is a very notable thing that can happen, and it happens frequently enough. It's not going to happen every year, but it happens, 1 out of every 3 years. So it's something that you'd want your like physical model that's making forecasts to be able to reproduce. So I think that the best argument I can give for why someone doing forecasting should care about these is from kind of a validation standpoint. If you have a prediction system that cannot reproduce these in autumn, at least in November, December, then you're probably missing something. If whatever your system is for prediction can produce these, that's a mark in their favor. And that, it's not a really strong endorsement, but it's a little bit of a reason why someone might care. All right, so you also asked about the southern hemisphere. I don't know Antarctic sea ice very well, so that is a very important caveat. That said, there are a few things I know about the Antarctic sea ice regime, and that is, one, there's a lot less multi-year ice. Number two, the polar jet stream around Antarctica and that storm track gets some really strong storms. And so just very, very naively then saying, I wouldn't be surprised if this happens more often in the southern hemisphere and it's not as much of an exceptional event and it's more run-of-the-mill. But I have not looked at any of the data to back that up. It's just intuition based on a few things I know.
All right. I feel like we've sort of tapped out for questions there. It's funny, as Dave asked about Antarctica, it came to my mind too when I wrote it on my notes here, and then Roger dropped a question about Antarctica as well in the chat. So similar line of thinking there. Anyways.
Antarctica is something I need to learn more about because it's a cool place, but I'm just stuck up in the north.
Yeah. Only you knew someone who knew a lot about Antarctica.
If only I knew someone who knew something about Antarctica, right? Yeah. For those of you not in the room, my wife studies Antarctica, so. Yeah.
Anyways, I think that brings us to a close. So thanks again. That was great, Alex. I really enjoyed the drawn out format of the talk today. Much better than the 12-minute version I've seen before.
Thanks.
Thanks again for volunteering. We really appreciate it. Again, just a note that this is posted on the IGS YouTube page, and there is a really nice record of all of these seminars available on there. We are off next week, but we are back in 2 weeks with Aditya Kular, who will be talking about the energy balance of ice on Mars. So we're going a little extraterrestrial there and looking at ice on Mars. So I hope you all join us again in 2 weeks and pay attention to CryoList and the other postings that promote this seminar series. We've got seminars booked all the way through to May with some really exciting speakers coming up. So I hope you can all join us. And that's it for this week. So thanks again.